6 or 12 chapters, something like that. So we finished chapter 2 last week, right? How many of you contemplated not coming back after that? It's a tough chapter, right? It really is. But it gets easier for a few minutes, and then it gets harder again, and then I don't know after that. I stopped paying attention. So today we're going to take a slightly different approach when we think about stuff in your brain, right? We took that very detailed look. We're going to zoom out just a bit, sort of skip over a few things that I don't think are that important, and then we will come back around to maybe some detailed stuff later. I'm hoping to get into chapter 4 today. I think that's going to be great for you guys. Really connect back to chapter 2 and make some sense. So chapter 3, structure of the nervous system. We think we already talked about that, but we're going to talk about bigger, broader features with structure. We'll also talk briefly about the development of the nervous system, right? Because that's kind of interesting. We'll go from there. All right, here are a bunch of words that tell you which way you're going. If you don't know them, don't worry about it. If you do know them, great job wasting your time learning those. Because you never see anyone like in their regular life going, I think I put that in the anterior of the refrigerator. It's just not terribly useful, right? Where this will be useful is when we start to talk about brain structures, right? They're going to have weird names, okay? They're going to have words like ventral medial prefrontal cortex, and that tells you something about where it's located. Doesn't really tell you anything about what it does, right? But should give you some idea about those first guys poking around in the brain. They had no idea what things did. They're like, hey, here's a lump of stuff. It's in the front, sort of in the middle, on the bottom. We'll call that the ventral medial prefrontal cortex, right? Because that's what all that kind of means, okay? So if you want to spend some time learning some of these words, that would help. But if you don't, you'll be fine. Sometimes you get the urge to slice a brain, right? It happens to the best of us. The brain is a three-dimensional structure, right? And so when you slice that three-dimensional structure, depending on which plane in which you cut it, you're going to get a different view, right? You're going to get some different idea about the shape of a nucleus or what the brain looks like. Typically, we'll cut stuff down the front. We'll call that a coronal section, right? Sometimes you'll cut things horizontally, like from top to bottom, and then you have your sagittal cuts, okay? Don't worry too much about that. We already talked central and peripheral nervous system. That's just some review for you. Here's a brain that we're going to slice. Is that better? Kyle, what do you think? You don't have a light meter. You can measure the light levels just to make sure that everything's okay. So here you go. Depending on which way you're going to slice that brain, you're going to get sort of different views. Not a big deal. This is an important slide. It's important because I want all of you to know you're not alligators. So this is really just me showing you the difference between you and an alligator. I know some of you are even more confused than I anticipated by this slide, but that's okay. What's really important about this is the neuraxis, right? So there's this idea that a lot of the stuff we're going to read about in the book, a lot of the studies we're going to talk about are going to be studies that were performed in quadrupeds. Okay, means you walk on 4 limbs. Most of us are bipeds. We walk on two limbs instead, right? So that changes some of those directions. It changes the relationship of the spinal cord to the brain, right? So if you think about our head and that alligator's head, they're both oriented the same, right? What's not oriented the same is the spinal cord. Ours goes up and down. Theirs goes horizontally, okay? So just kind of keep that in mind. You also have some other fun words with, doesn't work as well with humans, but there you go. We'll sometimes use rostral or caudal. Rostral means toward the nose, caudal means toward the tail. If you don't have a tail, just imagine where you would have one. And that's what caudal means. All right, who loves meninges? Nobody. Sort of? You're undecided? That's fine. We should talk about meninges briefly. This is a protective wrapping around your brain and spinal cord. You sort of have three levels: the dura mater, the arachnoid, and the pia. Has anybody ever dissected a brain? Yeah, it's kind of fun, right? Always ask first before you dissect a friend's brain. They may have been saving that brain to dissect later. You never know, right? If the dura was still on that brain, it's very tough, right, Lindsay? I mean, it's almost like, why did they wrap this in hard plastic? And you really wonder if it's actually a biological piece, but it is. It can be quite tough. So it's that outer. Dura mater sort of means tough mother, right? Some debate about whether or not that's like a mistranslation somewhere, but tough mother works, right? Why they call it the arachnoid membrane. If you start yanking on it, it looks like spider webs. The pia is very thin, easily destroyed if you're like chunking into a brain, but it follows the contours of the brain, right? So it'll kind of dip down in there. You've got cerebrospinal fluid, kind of like blood plasma, just a fluid, fills the system of the those ventricular systems. We'll talk about those as we need to. I just want to introduce you to these concepts today, right? This is not really a day where I'm going to go, hey, let's learn everything about the basal ganglia today. What I want you to get out of this chapter is, hey, there is a basal ganglia. We'll talk about what it does later, okay? Some of you may not have heard of these things before, so a nice little orientation is a good idea, right, before we start jumping into something. All right. You've got ventricles, you've got your lateral ventricles, your third, and then your fourth ventricle. Anybody know how you get from lateral ventricles to third ventricles? You have two lateral ventricles. That's 1 and 2, right? And then you go to your third. Not a big deal. Are there problems with your ventricles occasionally? Right? You can have what's called obstructive hydrocephalus. Everybody knows what obstructive means, right? This means water and head, right? So you're going to get your drainage spout blocked up, right? And it's going to cause the buildup of cerebrospinal fluid in your brain. It's pretty easy to fix. You just put in a brain valve, right? Just like, how many of you have a hot water heater? Okay, yeah, a couple of you, right? How many of you have hot water? Yeah, you have a hot water heater then, right? That's how that works. That's how you get hot water. Right? Most hot water tanks, they look like this. They're kind of that big round thing in that closet that's got pipes coming in and out of it, right? In case you didn't know what it was. I know, Zachary, right? Like some people don't know. They have a little valve typically on them, right? They have a little pop-off valve. When the pressure gets too high in here, there's usually a little tube coming down that'll drain the water out, okay? That way your hot water tank doesn't turn into a missile, which you don't want to do. You can do the same thing in your brain, right? You can just put in one of these little pop-off valves and let that CSF drain out if you get blocked up, okay? Here are your ventricles. Lateral ventricles here. Third and fourth, not a big deal. Here's a baby with a brain valve. See, I told you it was a real thing. If you get... one of the problems with your brain... So, well, let's back up a little bit. How many of you have ever had, you know, like your muscles? You've had some injury, you've had some swelling, you've had some issue, right, where you've you know, had inflammation or swelling. Anybody had something like that? I think everybody has, right? It happens all the time. Most of your other tissues, there's some ability for that to expand, right? So let's think about one of your leg muscles, for example. Let's say it gets injured. Let's say it gets a little swollen. You've got some stretchy tissue there, right? Like your skin that's going to expand, right? The sort of the confining part, right? The bone is down the middle, right? So it's not really confining that swelling or that stretch too much. Your brain is sort of reversed, right? We put the hard shell around it, and we put that skull to protect your brain, so we kind of wrapped it in that. Your skull does not expand, right? Not in any kind of real-time fashion, right? So if you needed to like suddenly expand a portion of your brain because you're having brain swelling or you've got some buildup of pressure due to that fluid, there's really only one way to do that, and that involves a circular saw, right? And you have to like cut a piece, and so that way your brain can swell out that hole, and hopefully it goes back down, and then they put a nice little lid right there for you, right? That's exactly how that works. It's a little more complicated. They wash their hands and keep things sterile, but you know, it's the same basic idea, right? And that's kind of brain surgery in a nutshell. Okay. So the problem is, anytime you have an injury to your brain that's going to cause swelling, if you have a brain tumor, for example, right? One of the big problems with brain tumors, and we'll talk about that later in the semester, is not necessarily the damage they're doing directly, but the indirect damage they're doing as they continue to grow, and they're taking up space and cramming the rest of your brain tissue up against the inside of your skull and causing damage to that, right? So if you can get that tumor out of there and you've got all that regular space, you know, your brain can actually do okay. So there you go. If anybody wants like preventative surgery, right? I always think about this, like you could put in like some little like accordion kind of things, right? And so like if your brain's swelling, you're just, I think about this, right? Like what if you're someone prone to head injuries? What if you're like a downhill skier? Those guys are prone to head injuries. So if you're, you know, thinking like I'm going to spend the rest of my life as a downhill skier, maybe I should put in, you know, some extra expansion there, right? Like little brain pop out. It's an idea, right? All right. So what do we need to think about when we think about development of the nervous system, right? How many of you have taken a human development class? Yeah, I bet that was interesting, right? Did you talk much? No? I'm going to make a note to tell. Who'd you take, Dr. Atkins? Oh, you're not going to admit to it now. It's okay. Oh, you did? Oh, really? Well, that's great. So you're going to love this class because our development section is like, it's not very long. I think it is sort of important to think about your nervous system during development. It starts very early in embryonic life. It actually starts out as a hollow tube, and it's pretty much a hollow tube once you get to be an adult too, right? Hopefully you've filled in some tissue, right, Sydney? But it's still a tube. Think about that ventricular system. It dumps right down into a tube that goes right down the middle of your spinal cord, right? So it's just a big hollow tube, okay? I like to point out it starts early. I don't want any hands going up right now, so just keep your hands wherever they are, provided that's not someplace causing problems, because I'm gonna say, how many of you have the capability to produce another human? Okay, like a number of you, right? I'm going to assume a good bit of you do, and if you don't, you're probably involved with someone who does or know someone who does, right? And that's capability of most humans in your age range. The other thing I want to ask, and I don't, again, want you to answer this, is how many of you are participating in activities that could lead to the production of another human, right? And obviously, hopefully not right at this moment, but perhaps at some other time, you know, when you're not in this building. I would say a number of you are doing that as well, right? My point here is, because the development of the nervous system happens so early in embryonic development, and you might not have even quite figured out that you're developing another nervous system, you may participate in other activities that might disrupt this process severely, right? And so what I want to caution you is, because you're at a time in your life when you're not making the best choices. And that's what you're supposed to do now. You're supposed to make bad choices and learn from those so that when you get a little older, you make better choices, right? And then you can waste your time telling someone else, like, don't make bad choices because they're not going to listen to you, right? How many of your parents have told you don't do something, but you did it anyway, right? They wasted their time because, you know, their parents told them not to do the same thing they did that they're telling you not to. It's a process, right? It's how things work. So my point is, this is like a real story and a real kind of take-home message. Be careful out there, right? If you guys are doing things that can create other people, make sure you're taking the steps necessary that if you do create another person, that person has the best chance possible to turn out to be a happy and healthy individual, right? If you're saying, like, I definitely don't want to grow another person inside my body, take the proper steps to make sure that doesn't happen. Right? There are a number of things you can do to make sure that doesn't happen, just participate in, 2 or 3 of those. It's always great to have, like an extra, it's a backup, right? So you put a spare tire in your car in case one of those tires goes flat, you got a backup, okay? So just keep that in mind. You all right, Kyle?
Yeah.
We're ready for that, were you? All right, so there you go. And hey, here's what's also really amazing. There are people who will talk to you about details on this if you want. I'm not one of them. So we'll just start there. And my assumption is, as a student here, you have like some free access to some of those people, right? Is that accurate? Yeah. And I think, I don't know that this is true, that you can still get like free stuff to make sure you don't grow other people. Is that accurate? Like anybody who wants to own up to that?
Do you have children?
No.
Okay.
Yeah. Not at all. I got a cat. I know, it's exciting, right? No plans for kids. No. And you guys shouldn't have kids either. Like none of them. None of you should. And I know most of you aren't going to listen to me, which is terribly unfortunate. Not about you individually, but just there's like a carrying capacity on this planet, right? And we're sort of exceeding that, so we need to start reducing our numbers. And you can do that by making smart choices, right? I'm not saying go out there and like, drown a bag of cats. I'm saying let's make smart reproductive choices going forward. If you don't need those parts, do things so you're not using them all the time, right? Like with your cats. Get your cats spayed or neutered. What's the cat going to do? It's not going to make more cats. A couple years ago, I caught 8 cats and had them spayed and neutered. How about that? All right. Here's a brain that's in a embryo. Goes through some stages. You add tissue. You get a nervous system. That's really what I want you to take away from this. I don't. I'm not going to ask you I'm only going to ask you a couple things about the development of the nervous system, right? This isn't one of them. This isn't one of them either, but I think the important thing to think about here is that you can map from the very beginning of the nervous system until it's fully developed, like where those cells go, right? Which is really, if that gets you excited, that's awesome, right? Because that's like the coolest, this is like taking, it's just really amazing. It's kind of like taking just like a bag of parts and just like shaking it, and then all of a sudden those parts know where they're going, right? Because of all these like chemical signals and these genetic signals, and it's just amazing. And then all of a sudden you reach in the bag and you like pull out an iPhone. You're like, wow, that was impressive, right? You just like put a bunch of like screws and pieces of glass in there, like the building blocks, and those building blocks knew where to go. And it's really kind of a cool process. And that's really all I want you to take away from that. Hey, here's something. You've got different divisions of your brain. I'm not going to ask you to memorize these. This sort of level of thinking is I don't know. Somebody's probably spent a lot of time driving that into you, right? Did anybody have to like go, like, what's in the telencephalon? I don't think that really makes a difference to you, right? You can memorize all the names and levels and stuff that you want to. Ultimately, it's got to come down to what the function is of those individual pieces, right? Do you know how they work together, right? Let's think about it in sort of a broader context. It's not important for this class to just go naming a bunch of things we want to get down. We actually want to think about what are the structures. We'll talk about all of these structures throughout the course of the semester. Today, again, I don't expect you to memorize what they do. I'm going to tell you briefly what they do so we can kind of think about that, but today's more about, there is a thing called the thalamus. That's pretty cool. We'll talk about that later, right? There's sort of another broad way that you can sort of break up your brain. There's what we call cortex, And we think it's so important that we call everything else subcortical, right, below the cortex. It's not whatever you call the middle part, and then above that, it's the above part first, and then what's below that. The interesting thing about your cortex, that's the wrinkly part on the outside of your brain. That's really the big difference between you and a lizard, right? Because a lizard does basically everything that you do, right? It breathes, it eats, it walks around, it makes other lizards, right? It does all of the same basic behaviors that every other species does, right? So there are certain problems it's solving, certain things it's doing that are going to be pretty much identical from species to species, right? The different part is our sort of behavioral flexibility. And that's what we want to think about. That's what's really going on out here in cortex. That kind of wrinkly outer rind of the brain, right? The bigger your cortex, in particular your frontal cortex, we like to think of us as being smarter, more cognitively flexible, right? Sort of lines up that humans have the biggest frontal cortexes around, so it's like, hey, we must be pretty cool then, right? So if you have a big frontal cortex, that makes you cool. Little self-serving as a definition, but we'll go with it because it works fairly well. Okay. Over time, your cortex gets thicker. You add layers. Most people will tell you there are 6 layers. There were 6 layers of the cortex, and then all of a sudden the cortex made more layers. No. What happened is somebody got a better microscope, and they realized there are actually more layers than 6. The problem is for like 100 years, they've been telling everybody 6 layers. So they're not suddenly going to go and go like, well, they're really 9. They're going to go, nah, we'll just do sub-layers, you know. So like layer 4, for example, has got like a couple sub-layers, and I'm not going to ask you to worry too much about that. I think people like this 6-layer story. The reason they like the 6-layer story is there's another structure we'll talk about later that they also say has 6 layers, but in fact has like 12. And that's a whole separate story as well. But they love this 6 business, right? And they're like, oh, it's got 6 layers. So there you go. Whatever. All right. You've got stem cells. That's kind of cool. These are the cells in your developing brain that are like, hey, I think I want to be a nervous system cell, right? And we send them over to the advising office. And in the advising office, they say, hey, you know what you're really suited for? You're really suited for that olfactory cortex. So head over there, you know, sign up as a, you know, I don't know, nursing major or whatever, right? So they go to these different directions. The cool thing about this, again, is these cells have, they follow these cues, right? They have genetic cues, they have these chemical cues. They move around, they migrate, they go different places. It's really a fascinating sort of situation. Human brain development takes a bit longer than brain development in other species, either before birth and after birth, right? Both of those situations. We already talked about humans being born sort of half-baked, right? Because they have to fit out the birth canal, okay? There's a lot of development that happens before, a lot of development that happens after. A good bit of this happens in the cortex, right? It takes a while to build something complex, okay? So we're going to spend more time doing that compared to other species. All right. Are there problems with brain development in humans? Absolutely. Some things can go haywire. Sort of depends on genetic issues, environmental conditions, right? So what's one of the sort of environmental conditions you guys all know about that can develop nervous system development? Think about alcohol ingestion, right? And I know there's always this story like, oh, well, you can drink this much during this time. Listen, I don't know all of you, but I know some of you. And if you're going to have kids, don't take any chances, right? They need all the advantages they can get. Let's just be honest, okay? So put them out there on a good foot, and you know, if you think you might be pregnant or you're trying to get pregnant, you know, stick with carbonated water. That's a good idea, right? Anybody getting pregnant soon? I need to know how many people I might buy stock in a carbonated water company. Great. So we should talk about this concept. This is one of the things I'll ask you about when it comes to development of the nervous system. It's called synaptic pruning. Later we'll talk about learning and memory later in the semester, and we'll kind of revisit maybe this idea at that time. But right now you want to sort of think about this. What's interesting is when you're younger, like let's say 5 or 6 years old, you actually have more neural connections than when you're older. And that sounds like, and I mean older like 14, right? That sounds like you're going downhill, right? Like, oh man, 14, I'm already starting to lose brain connections. That's a bad idea. Well, it's not, right? How many of you have ever traveled, I know like all of you go to Beckley all the time, right? No, nobody. Mendeja, how many times have you been to Beckley? Too many? Four or five, yeah. So if you're going from here to Beckley, what's the best way to go? You don't know. Yeah, right? Which doesn't make a whole lot of sense because it's north of here, but we'll let you by on Y77 South. It's always a confusing one, right? So you're going to take an interstate. It's a direct path, right? That's the fastest, most efficient way there, right? Prior to the structure, the building, right, of that interstate, what was the best way to get to Beckley? All right, yeah, turnpike. So let's get rid of the turnpike, and then you're left with these roads, right? Here's you getting to Beckley. Does that make any sense at all? No, that's why they put in this road. Okay, it's what you're doing in this synaptic pruning process, right? You're getting rid of useless, inefficient connections so that you can have a streamlined, more efficient process, right? Hey, who remembers that time I told you your brain is at any given moment getting like 25% of your blood supply, right? It's using a ton of energy all the time. If we can get rid of useless, redundant connections, that sounds like that's pretty cool, right? And we can maybe save some energy there, okay? Does that make sense to everybody? So you're going to do this synaptic pruning process. You're going to get rid of the things that you're not using anymore. You're going to clip those out so you can keep that efficient connection. Go faster. Yeah, here's a, I guess this slide's kind of interesting. You've got a bunch of stuff happens, then you fall out of a uterus, and then a bunch more stuff happens, and then you die. So there you go. Should we talk about the forebrain? I guess. That's the largest section of the brain. Handles a lot of interesting stuff. We'll talk about telencephalon, diencephalon later. Not a big deal. We should talk about a sulcus and a gyrus, right? A sulcus is kind of a dip in the brain, right? And the gyrus is the sort of bulge, right? So you have these wrinkles, right? You have like hills and valleys. Sometimes the hills and valleys get really big. You might call something a fissure at that point, but you got the basic concept. Spinal cord comes out of the back of the brain. How do you know when you get from the brain to the spinal cord? It's like a big road sign that says now you're in the spinal cord. Structure changes, right? There's some structural changes you could think about. Your spinal cord does not go all the way down, right? Goes down most of the way, part of the way, and then there's something called the cauda equina, which means the horse's tail, and that's what anchors, or that's what is the last like jumping off of all of the nerves that need to go to the rest of your body. You've got the filum terminale anchoring that spinal cord down at the bottom, right? You don't want to go breaking that. It's probably pretty difficult to do. Some people do it sometimes. It can actually cause some shearing of those spinal nerves, right, as your spinal cord would slide up and they would get clipped off coming out between your vertebrae. So everybody walk home gingerly. There you go. Hey, what about cortex? We talked about cortex. A good chunk of cortex is devoted to sensory processing, right? So these sort of three regions, vision, hearing, and then body senses. There's also a good bit of cortex devoted to motor commands and movements, right? We are a rather mobile species, so it makes a lot of sense to have a chunk of our brain devoted to that. We also have a good chunk of the brain up here devoted to sort of like planning actions and like math and thinking of ways to, you know, avoid that annoying person that you know you're going to see next week. Okay. Yeah. Rats don't have that capability. They have to see the annoying rats all the time. They can never think of a good lie to get out of a bad rat party. But humans, we can do that because we have that nice frontal cortex, right? We can make up good stories. Oh, geez, I'm I don't know, getting the transmission polished in my car, and I can't make it. Don't worry about that slide. That's just a human brain. And you've got these like 4 lobes business, right? I'm not going to ask you about the 4 lobes. If you know about the 4 lobes, great. If you don't, they still work. Work just as well. Here's your brain if we slice it down the middle, right? This is kind of interesting. We should talk about this big bundle here. It's called the corpus callosum. It's really important for like the left side of your brain to know what the right side of your brain is doing, okay? And this big fiber bundle is communicating information back and forth, okay? You can absolutely live your life without one of those. Probably 1 in 600 kids are born without a corpus callosum, which is kind of interesting. They're called acallosal. No callosum. Corpus callosum. So if you're thinking about that, how many students does Marshall have? Right, that's a number, right? So how many people are walking around on this campus that don't have a corpus callosum? Something to think about, right? And they seem to do just fine. You're not going to know, like, I bet he doesn't have a corpus callosum. Now, as an adult, if you get your corpus callosum cut, which you're welcome to do, you would notice a difference, right? You would start to do some weird things. Why might you have your corpus callosum cut as an adult? The biggest reason is if you have intractable epilepsy, right? If you have epilepsy or a seizure disorder and they have tried almost everything else. I can't think of anything they would go like, that's worse than cutting your brain in half. Because that seems to be pretty invasive, right? They got to cut open your skull, they got to slice your brain down the middle, they got to sew you back up, and then they got to send you out there in the world, right? That's a rather invasive approach, but they will do that from time to time. They don't do it very often, and afterward you would notice some interesting things, particularly with the sense of smell, which doesn't really cross over very well. You can do some weird things. Also, some other things you can do. This is kind of a fun one. If you hold up a sign, like you kind of keep people from information from getting in both eyes, you just send information through one. You hold up a sign that says, hey, eat a banana, and they'll reach out with their other hand and they'll eat a banana, and then you go, hey, why are you eating a banana? And they'll go, well, I must have been hungry. Because the information they're reading is not getting over to the other hemisphere as it should, right? So they'll make up a story. It's called confabulation. Right? And what humans are really great at is making up a story after the fact. Right? We will often make a decision. That decision is probably emotional, unfortunately. And then we will try to back that up with all of that great brain power that we have hanging out there in the front, right? How many of you are New England Patriots fans? Keep your hands up. I'm going to fail you. So, why are you in New England? Are you from Boston? No, see, there's a problem. I mean, you see the shirt he's wearing? He's wearing a Cleveland shirt. I mean, that's just... Are you from Cleveland?
No, but I think they're watching Boston.
That's nice. I mean, that doesn't make up for, being a Patriots fan, but, I'm not going to make fun of you too much. But why are people sports fans? Yeah, if you're from that city, right, that makes some sense, right? You're like, oh, well, I'm so sorry you're stuck with, whatever team it is. But if you're not, why? You make some emotional decision and then you back that up, right? And you go like, well, man, I love the Jets because there's no good reason there. Let me try another team. But you try to make, right, Kyle? You try to make decisions, right? So you have a sports fan thing you want to share? Yeah. I just in the tiger stripes. I don't know, right? I mean, there's just not. They never win. Well, they won once. What was that time? It was like back in the '80s. You probably don't remember that. A game. They were best football team in Southern Ohio. It's after the Iron Tanks went. That's a joke that nobody got, but it was such a great one. This is like the 100th anniversary of the Iron Tanks. Anybody know that? Nobody knows that. Nobody knows the Iron Tanks. Guess what's going to be a bonus question on the exam, Kyle? Go ahead and put it on there. It's going to be about the Iron Tanks. And somebody's writing it down. Like one person's actually taking a note on this. None of the rest of you are. And that's disappointing. Now it's going to be 2 questions. I can't wait until we get to the second exam. I can ask about head injuries. I'm even going to ask more. They were a professional football team. Anybody been to Ironton, Ohio? Yeah, they used to have a professional football team. See, now it makes sense, right? Yeah. So confabulation, you'll make up a story, right? You make up a story after. Why that guy eat a banana? Well, he saw a sign that said eat a banana, but in no way was he able to get that information from one hemisphere to the other so that he could get that output to you like, hey, I just saw a sign that said eat a banana. So you make up a story. I must have been hungry. That's why most people eat bananas, right? More about lobes. Again, I think one thing to take away from this is like all of this area back here of cortex is sensory, right? Actually, this is sensory too. This little bit is motor. Like that's just motor output, right? So there's a bunch of other motor planning areas we'll talk about later. A bunch of other sensory areas like collecting information, but that's kind of the output. And then here in the front is all like, oh, what am I going to have for dinner today? And you know, that higher order planning stuff. We'll learn about all of that homunculus stuff some other time. There's your lobes, corpus callosum. We talked about that. More stuff you don't have to worry about. This is the corpus callosum. Someone has artificially colored this so you can kind of see those areas pop out. They're trying to color code this so you can see different parts of cortex that's getting information through the corpus callosum, right? So different information streams. Not a big deal. All right, I'm not going to ask you too much about this stuff. What I would like to do now is sort of go through some broad organizational categories of your brain, talk briefly about some of the important ones, just so you know later in the semester when I say, oh, limbic cortex, you've heard that before, right? It's not like a brand new word you have to learn then. We're going to learn the brand new words now, and we'll add a little bit more function and detail later. All right, limbic cortex, your limbic system is going to be really involved in sort of emotional aspects. The hippocampus is largely memory, consolidation, not storage. We'll talk about that some point in the future. Your amygdala is sort of your fear nucleus, right? We'll spend a lot of time talking about the amygdala later as well. It's from it's from the word for almond. It's almond shaped, right? Folks who were very early looking at brain structures, they often named them things that based on their appearance. They had no idea what the function was. Right? They're just like chopping into a brain, just like randomly like slicing stuff and go like, hey, that looks like an almond. It has nothing to do with eating almonds, right? In no way is it like you know, something related to almonds. But there you go. Questions about that? Those are sort of the, we're not going to really talk too much about the other areas in the limbic system. This is giving you an idea of where these things are located in your brain. Limbic cortex is here. Your amygdala is here. Then your hippocampus, it actually looks like a seahorse, which is why they call it hippocampus. Anybody heard of a hippodrome? What is it? A hippodrome? It's like a big stadium for horses. So you know, that's where we're getting the hippo there. What about the basal ganglia? We'll actually talk a good bit about the basal ganglia, right? There are a number of sort of well-known neurological issues that run through the basal ganglia. How many of you have heard of Parkinson's disease, Huntington's disease, OCD, autism implicates the basal ganglia. We'll talk about all of that. A lot of things that are related to repetitive movements are going to run through the basal ganglia. It's got some components underneath of that, your caudate, putamen, and globus pallidus. Not too big of a deal. We'll talk about those as we need to when we get later in the semester. There's another couple structures that are important, the thalamus and the hypothalamus. You would think that they're sort of functionally related, right? Because they sort of carry the same name. They're not really. Thalamus is sort of like, oh, it means it's like in the middle of your brain inside, and hypothalamus means it's kind of below that thing that's in the middle of the inside of your brain. They're not necessarily related to the function of those structures. Your thalamus is a sensory processing area. When we talk about sensory systems, we'll talk a lot about things running through your thalamus. Different parts of your thalamus are devoted to auditory or visual or somatosensory, and you have different kind of components there. The hypothalamus, I might argue the hypothalamus is one of the most important brain regions in terms of your day-to-day function and behavior. And the reason I say that is the hypothalamus really controls hormone release. Okay. So we'll talk a lot about hormones and how hormones drive your behavior later. How hormones and circadian rhythms, how many of you have heard of those? Okay, circadian rhythms are going to be controlled by structures in the hypothalamus. Again, the hypothalamus is really a collection of 30 different smaller nuclei, right? So if you go like, oh, my hypothalamus is screwed up, that gives you about as much information as saying, oh, my house is screwed up. Hey, what are you going to do? What problem is that causing you, right? The hypothalamus is a big structure. I mean, it's not a big structure in terms of size, but it's a big structure in terms of its impact on function. And there you go. There's your thalamus. Your hypothalamus is below that, and then your basal ganglia kind of wrap around either side. Thalamus is sensory processing. So it collects, it's sort of, well, it's a long story, but I'll tell it to you as slowly and painfully as possible. Cortex was originally viewed as like the coolest part in the brain, right? Like, oh, everything up until cortex is just relay station. Then some folks started looking at the thalamus and they're like, oh no, the thalamus is actually doing some serious processing of sensory information, right? And they're like, okay, so the thalamus is doing that first level of processing. Anything before the thalamus, not anything going on. Then there's some folks who are like, you know what, really, there's like some processing going on out in the retina, out in the cochlea, so maybe there's just processing all around, right? But the thalamus is one of the early big players in sensory processing, and it's for different sensory streams. Is that good? Awesome. All right, again, the hypothalamus, tons of behaviors related to survival. There's your 4 Fs. All of those seem pretty important, right, to the survival of you and the species. All right, questions? No. Great. We don't really need to know about that. Don't really need to know about the tectum and tegmentum. I'm not going to spend too much time there. Let's see. The superior colliculus we might talk about at some point. It's sort of a sensory integration area, right? How many of you have ever heard a noise and turned your head? Your superior colliculus was probably involved there. What's out in the tegmentum? A couple areas. The periaqueductal gray is involved in pain. And then the substantia nigra. In fact, it's the nigrostriatal pathway that kind of kicks out in Parkinson's disease, right? So the dopaminergic cells in that pathway die. You're not releasing dopamine into the basal ganglia. We'll talk in detail about that later. And that's what causes the movement disorders, or the symptoms of the movement disorder, Parkinson's. What about your hindbrain? Yeah, this is an important spot. This is, I kind of refer to this area as the idiot box. This is where we put all the important stuff that if you had to think about it, you'd screw it up, right? This is where we're going to control your breathing and your heart rate, right? Blood pressure, right? How many of you are thinking about controlling your blood pressure right now? Nobody, thankfully, right? Because if you were, you wouldn't be able to focus on the really important things I'm saying, right? Because you'd be back there going, wait, no, that blood vessel needs to dilate just a little bit, and you would not, you'd miss so much, right? You'd probably be eaten by a hyena, okay? But even hyenas figured out, we don't need to think about that stuff, just put it back there in the hindbrain. There's also this guy called the cerebellum. It's sort of a movement area. It's really important because it's like feedback. How many of you have ever done something and then you wanted to like realize you did that, right? That's the cerebellum's job. So as you're moving through the world, you're just like walking around doing your thing, whatever that is. The commands coming out, right? There are commands coming out of your brain going like left leg, right leg, whatever. Wave at this person. I think I know. Oops, I don't. So get embarrassed. Right? So that's Caitlin, that stuff's going on. But you need to know that you did that, right? Because when you're like stepping, you need to know like, oh yeah, I actually took a step. Because if you didn't take a step, what do you need to do? You need to take another step, right? You need to take that first step. So the cerebellum is giving you that feedback information. Okay? The cerebellum is the guy who stops you from like stepping through the floor. Have you ever walked along and you thought it was flat and then there's stairs and you step and you're anticipating that feedback, right? You're anticipating I'm going to hit the ground, but you don't. And most of the time, hopefully, you don't tumble all the way down the stairs, right? You kind of go down and like you catch yourself, okay? Your cerebellum is working there, right? It's saying, oh, guess what? I thought I was going to do something. I didn't. Let's just put the brakes on and see what's going on because there's a mismatch in information. There's a small problem with the cerebellum. It's very sensitive to alcohol, right? This is why when you drink alcohol, you become like an Olympic gymnast. It happens all the time. You think you're an Olympic gymnast. In fact, you're just like rolling around like a baby. You see it, right? There's a direct correlation between how much you have ingested in alcohol and what you think your athletic capabilities are, but in fact what they are. And this goes down this way. This is what happens. I know, right? You're surprised, right? Didn't realize this. There's stuff in the back of your brain. And there's something that comes. Once you get out of your brain, you're into spinal cord, right? It runs all the way down. Nerves come off. They go places. They send out commands. They get information back. There's like this whole story about dorsal and ventral root ganglion. We're not going to talk about that. Cranial nerves. We should probably spend a tad bit of time talking about cranial nerves. You got a bunch of nerves coming off of your brain pretty early. They mostly handle stuff in the like head and neck region. Okay, some of those go to your eyes. Some of them go to other places. Some of them are mixed. We say they handle sensory and motor information. Some of them are only doing one or the other. Not a big deal. Don't worry too much about this. Oh, we should talk about the autonomic nervous system, though. Okay. This is the system that gets you hyped up and the system that brings you back down. Okay. It's got two divisions. You've got your sympathetic division and your parasympathetic division. Sympathetic, again, right? It's going to do things to increase your heart rate, increase the release of nutrients to your body. It's going to do all those fun things. Okay. Things like epinephrine and norepinephrine, right, that are released. It's going to be part of that sympathetic division. Norepinephrine and epinephrine are also known by another name, noradrenaline and adrenaline, right, coming out of the adrenal cortex of your kidneys. How many of you have heard of an adrenaline rush, right? Unfortunately, you can't just stay in an adrenaline rush all the time. There's some serious problems with that, right? Like you'd never sleep, you just run through walls, and then you'd probably die of a heart attack in a day and a half. I don't know if that's a real number, but we can try it. So you have to have a parasympathetic system to bring you back down, right? It kind of brings you to that relaxed state. There's a picture of cranial nerves. That guy looks so interested in posing. Spinal cord, no worries there. Any questions about that? Great. It's not too complicated of a chapter. But I would like to spend a little bit of time on chapter 4. All right. Psychopharmacology. Show of hands, how many of you have taken drugs? Yeah, probably all of you have. Haha, that's an anybody taking Tylenol? Yeah, that's a drug, right? Anybody, if you've ever been to Starbucks, I don't even want to know what drugs they give you there. Caffeine, that's a drug, right? What is a drug? A drug is any chemical that has some effect on your physiology, right? It's that simple. We like to throw the word drug out there for like bad things, right? Or like, oh, how many of you have done drugs? The first thing you think of is like opioids or cocaine or something, right? But there's so many other drugs that you ingest on a daily basis, right? How many of you have ever had an energy drink? There you go, big drug users. Right, Kyle? Just agree with me. I would like to say you're like Ed McMahon and I'm Johnny Carson. No one's going to understand that. Well, maybe someone does who accidentally stays up late and watches, like Time Life commercials. But maybe we're more like Conan and Andy, right? Sure. See, if I say so. That's the job. Yeah, if I say so. Let's talk about drugs, right? Why not? We'll talk a little bit about basics of psychopharmacology. We'll talk a bit about sites of drug action. And then this is going to lead us into the concept of neurotransmitters. And briefly, we'll touch on neuromodulators. We'll talk about those just a bit, but not too much. They're a little more complicated. All right, so here we go. What is a drug? It's an exogenous chemical. What do we mean by exogenous? Outside the body, right? It's something you create outside, or something that's not created by you, something coming from outside that you've put in your body one way or the other. And it just alters the function of some cells. It's that simple, right? That's all a drug is. Drugs are not things you create inside you. Now, what's really interesting is there is a very direct connection between exogenous chemicals that have an effect on your body and the endogenous products that you produce, right? If something you take can affect your body, there is something you create inside your body that's very similar, right? Because it has to work on that same system. And what we're going to think about in the brain is we're going to think about receptors, okay? So if you take a drug and that drug changes the way your brain cells work, that means you have a receptor that fits the structure of that drug. Why do you have a receptor that fits the structure of that drug? Because you make a chemical very similar in shape to that drug that works on that same receptor system. Okay? It's that simple. So there you go. What does a drug affect? It's going to change either a physiological process or behavior, right? That's what we're kind of thinking about. Although to change behavior, you sort of have to change physiological processes as well. So kind of one and the same. Here's, again, very complicated definition, site of action. This is where the drug interacts with the body and changes some process of those cells. Okay? That's the site of action. That's all it means. It's not a big deal. All right. So, when you take a drug, you've got to get it in your body. It's got to do something in your body. You got to turn it into trash, and then you got to dump the trash out. Okay? It's a 4-step process, right? So, we have to absorb the drug. Okay? There are many ways you can take drugs. We'll talk about those. Once the drug is in your body, you have to distribute that body. That's a much easier story, right? What's the easiest way to distribute things through your body? FedEx. No. Your blood vessels, right? Blood goes just about everywhere. If you don't believe me, get a knife and start jabbing. Blood will squirt out, I promise you. That's the thing you can do. I wouldn't recommend it. Find a close friend who will let you do these things to them. And, right? Or, random stranger. Think about it all the time, yeah? There you go. Once that drug gets somewhere, it's going to do some business, right? But eventually it's going to get somewhere to be metabolized. And what do we mean by metabolized? It's going to be changed from the structure that it is into something else, right? Most of the time this is going to happen in your liver. You've got a bunch of enzymes there that break things apart. That metabolized version of the substance you took is not effective, right? It's not going to do any action, and it's a lot easier for you to grab and toss out, right? And it's going to be excreted. Typically, this is the work of your kidneys. I believe it was a week ago I told you something very, very enlightening, and that concept that I delivered to you was lipid solubility, right? We talked about the blood-brain barrier. Okay. Metabolites of a drug need to be less lipid soluble than the drug. If they're not, guess what happens? They slide right out of the kidneys. Why? Kidneys are made of lipids. Well, they're made of cells, which are made of lipids, right? Okay. And if something is lipid soluble, free pass right through lipids. Okay. You need to make it less lipid soluble so your kidneys can hold on to it, and then you can send it out to the world in your urine. It does. It does. Well, they got to be fast before they get to the liver. Right. So and we'll talk about that a little bit. There are things called prodrugs that you'll take. So sometimes you're going to take something that's not active, and then when it goes through that sort of first metabolizing step, then it becomes active, and then it's got to come back around a second time to be inactivated. So there are times where that's going to work. There are also things you have to think about with like stomach acid. So there are a number of drugs that you have to bypass that, right? But if you inject a drug directly into your blood supply, for example, right, which IV is a pretty common route for a lot of drug administration, that's going to travel around your body some distance before it gets to the liver. Some things are going to get in the liver, and they're going to still kind of slip through, right? Because it's all like statistical probabilities, right? So what I always like to say is whatever is ever going to happen in your body is happening right now. It may not be happening at a rate that's going to make a difference, right? So these things are happening. So when you send a drug through and it goes through your liver, it's not like 100% of that drug instantly gets converted into its inactive metabolites, right? There's some statistical probability because that drug molecule's got to run into that enzyme molecule. That enzyme molecule and that drug molecule have to line up just right. They got to crack apart, right? It's got to fall apart and then not accidentally like come back together, which can happen, right? So there's like all kinds of like random things that can happen. Now most of what's going to be happening once the drug gets to your liver is those enzymes are going to chop that up, assuming you have functional enzymes that work. Some folks don't. There's genetic variability in enzyme function. Particularly, there's a group called the CYP that if you have some genes that are screwed up there, they're not going to be breaking down stuff. Okay, don't have to worry too much about that. There's that 4-step process. We talked about that, not a problem. We should talk about routes of administration. We're going to spend a little bit of time here thinking about routes of administration, why you take drugs different ways, how that has an effect on the action of that drug, right? So, how many of you don't have to raise your hands, but how many of you have had an IV before? That's a fairly common thing, right? I mean, lots of folks have IVs. I doubt many of you have had an intraperitoneal injection. That's an injection into the gut, right? Some folks may have. That's not a terribly common way to deliver drugs in humans, but it's there. Intramuscular injections. Probably a lot of you have had those. How many of you have had a flu shot? Yeah. Where do they put flu shots? Right in the deltoid, right? So it's going to be an intramuscular injection. What about subcutaneous? It's going to be kind of right under the skin, right? Okay. Oral administration. Take an Advil, right? Take a pill. Okay. Sublingual, this is different. Okay. Sublingual is different than oral administration. Okay. Some people put, there are things you can put under your tongue and they dissolve, right? There are a variety of medications that work that way. There are a variety of non-medications that work that way. You can put under your tongue, you can dissolve them. Why is that different than oral administration? Oral administration has to go to the stomach. Okay? That's where it goes. Mouth to stomach. Bingo. Sublingual administration is being absorbed into your blood supply through a mucous membrane. Okay? That's why it's a different process. Okay? You're not swallowing that. It's not going through your stomach. It's not got to be absorbed into your intestines, right? It's going directly into that blood supply. There's also intrarectal administration. Okay? This is when you put something in the outspout, right? Why might you do that? This is particularly useful for folks who can't swallow. Also, if you are nauseous, right? Let's say you want to take a medication that fights nausea, but you got to take that as a pill. Where's that pill going? It's going down and right back up, right? It probably didn't do you a lot of good. If you can take something intrarectally, you can get that absorbed into your bloodstream, right? What is the main job of your intestine? To suck things out of your food, right? To suck nutrients out. So you can put things in there and it'll pull it out. They don't typically go there first.
If someone snorts some drugs, which one of those does that count as?
None of these. I got another slide. Okay. Actually, snorting is very similar to sublingual, right? And the reason for that is, again, you're getting into those mucous membranes and you're absorbing through that mucous membrane, right? So that's what snorting would do. A lot of folks will get snorting and inhalation confused. You would think that's the same. It's all going in the nose, right? If you're breathing something in, possibly, but you're not. Inhalation has to get to the lungs, right? So you have to get that vaporized material to your lungs so that your lungs can pick up those molecules and send that out to your body. Snorting is, again, different because snorting is just going into a mucous membrane, okay? So mucous membrane, intrarectal, intranasal, and sublingual are all really sort of the same. They're different places, obviously, but it's the same process. You're getting into that mucous membrane and crossing that into the blood supply. What about topical administration? How many have you rubbed yourself up with a bunch of medication? Nobody's gonna. Poison ivy, okay. I was thinking something like lidocaine. Anybody used lidocaine before? Nobody's going to admit to that. Anybody used, perspiration? No, not perspiration H. That's for something else. Thinking about something else in that same category. Bengay. What about Tiger Balm? You use Tiger Balm? I thought so, right? As a tennis player, you got to use Tiger Balm. There you go. I was thinking like pain relievers, right? A lot of folks will rub on Icy Hot. There you go. That was it. Burn creams, topical, right? So you're going to put stuff on. There's also transdermal, which is different, right? Who remembers that time I was telling you about doing things to not have kids, right? There are a number of ways to get birth control medication into your body, right? Some of those are patches, right? That's going to be transdermal, right? So you can put on a patch. Those hormones will be absorbed through your skin. That's a little different process too. What about intracerebral? What's that mean? Yeah, we're going to squirt that right in your brain. Again, that's if we want to bypass that blood-brain barrier. Also, sometimes we have to put things directly into your ventricles. Okay. Now, why might we choose different routes of administration? Well, sometimes there are drugs that won't survive certain delivery methods, right? There are drugs that will not survive oral administration, okay? Once they get in, the stomach acid's going to destroy them before they have time to be absorbed and go out and do their business. So you might want to bypass that. Sometimes you need a drug to act faster, right? You want that to happen immediately. Okay, if you think about that transdermal kind of thing, that's a slow process, right? I don't know how often you put on one of those patches, once every whenever. Right? And they last for some extended period of time. If you needed that drug to work faster, you know, like let's say you're having an allergic reaction to peanuts. I don't know if anybody's allergic to peanuts, right? You're going to like put on a patch and wait a month to try to like breathe again. That doesn't make any sense, does it? So you need a faster route of administration. So here we go. Here's a great graph for cocaine, right? We're showing here 4 different methods of cocaine administration and how quickly there's a spike in the concentration of that drug in your plasma, right? And so when you look at IV, inhalation, intranasal, and then finally down here we have oral, right? It's a really popular way to take cocaine, those cocaine pills. No, it's not, right? Why are cocaine pills not popular? It doesn't work fast enough, right? If you're someone who's using cocaine, you want that cocaine effect immediately, right? You don't want a delay. In fact, if there is a major delay between when you ingest a drug and the effects of that drug, you're not very likely to become addicted to it, right? Okay? Because it takes so long. So there's not that timing, right? Learning is all about timing, right? And so if you do something and then you get an immediate feedback, then you tie those two things together, right? This is one of the problems with coursework and grading, right? How many of you have taken an exam in somebody's class, Laura, and they didn't get their exams back to you for like weeks, right? When that happens, well, you can't remember, like, what was I doing? Maybe I did well on the exam, maybe I didn't do well on the exam, okay? Well, what were my behaviors leading up to that exam? Well, I've forgotten now. It was 4 weeks ago, right? So if you don't have that feedback close enough, learning that makes it difficult, right? Now, it's not so important for you. That's why it can take forever to get your exams back. You're adults. You should know what to do to get good grades on exams. But if you're like a 7-year-old learning long division, right, that immediate feedback about your performance is really, really important, okay? So don't, I don't know if any of you grade long division papers from 7-year-olds. Do they teach 7-year-olds long? I don't even know. When do you learn long division? Are you 7? What grade are you in when you're 7? You don't know anything about kids either. I'm hearing like 4th and 2nd. I feel like something's not right there. I think the consensus is 2nd grade. Really? That's the problem. You need to learn long division when you're 7, not when you're 9. So, there you go. IV is obviously going to be, you're putting it right into your blood, so the spike in blood supply is going to be immediate, right? This is intranasal. Intranasal is pretty quick, high spike, but inhalation actually gets a pretty quick spike as well. Your lungs are really great at absorbing chemicals. That's how you exist, right? When you suck in air, you pull out the oxygen pretty quickly, right? If it took you a long time to pull out the oxygen, you die. Okay, so that exchange has to be pretty rapid. That's why inhalation is a really rapid way to get in drugs. And so what you can take away from this is you can look at sort of, IV, inhalation, and intranasal are some of the more popular ways that someone might ingest cocaine. Not oral, and the reason for that, again, is that shift in time, right? That's almost an hour later that you get the peak of concentration in your blood supply. If you do something now and then you do it, an hour later, you're like, wow, man, I'm feeling something now. Like, what was I doing just 2 minutes ago? I was tying my shoes. I bet tying my shoes gives me a good cocaine high. And then you try tying your shoes again, and guess what happens? Nothing, right? You're like, well, didn't learn anything that time. So there you go. If you want to become addicted to something, make your feedback as immediate as possible. Well, that's not a bad thing. Like if you want to be, maybe you want to be addicted to studying, right? You want to reinforce that behavior. You need to make sure that the reward is as close to the action as possible. Right? Now, don't worry about that. All right, so we've absorbed a drug. We've completely skipped over the distribution part because that just happens, right? You absorb the drug, it eventually gets into your blood supply. Once it's in your blood supply, it's the same time course, right? It just goes to wherever and it does its business. Okay? Then we have to deactivate it. Again, typically this happens in the liver. Those enzymes will deactivate that drug. They'll take that drug, crack it into two pieces, and those two pieces are not going to have an effect on your cells, and they're not going to be lipid soluble. That way we can bundle them up and put them into your kidneys, and you can excrete those, right? Sounds exciting. How many of you love to take drugs that are effective? Well, like everybody should, right? Because why would you take a drug that's not effective? That's a waste of time, right? When we think about drug effectiveness, one of the things we want to think about is that dose-response curve. And there is a dose-response curve for every drug. It may be shaped differently depending on that drug. Here's the basic idea, though. You take more of the drug, you get a bigger response, right? Now, how much bigger of a response might be different from drug to drug, okay? There's also something called the therapeutic index, right? This is the difference between the dose that'll make you feel better, whatever that is, you know, whatever symptom you're trying to treat, and the dose that will kill you, okay? So you should probably take something somewhere in there, right? You want to take enough of the drug to alleviate the symptom, but not so much of the drug that you die. Makes sense, right? The wider that therapeutic index, the safer the drug. Let's think about Advil for a moment, right? How many Advil do you have to take to die? Well, you have to take so many that your esophagus is choked up and you can't breathe, okay? Because you can take, like, I don't recommend it, right? Long term, there's some problems. But if you take a handful of Advil, it's not going to hurt you, right? Immediately. You're not going to see any sort of immediate issues. You're not going to die, right? What happens if you were to take, like, a handful of, you know, maybe you take, like, a whole handful of oxycodone, right? What's that going to do to you? That's going to be a serious problem, right? You might actually stop breathing, okay? Because morphine and morphine derivatives, your opioids, one of the problems is as you take more of the drug, you're more likely to have respiratory problems. You're more likely to stop breathing, right? And so then there's some serious side effects. So that's a pretty narrow, that's a much narrower therapeutic index, right? The amount of morphine that you need to take for symptom, you know, pain relief, and the amount of morphine that you take that's going to cause you to stop breathing, the distance between those 2 points is much smaller than the amount of Advil or you know, ibuprofen that you're going to take that's going to alleviate some muscle pain, and the amount that's actually going to be fatal, right? So those are much farther apart. Much safer drug, right? A great example, like LSD, very safe drug in terms of an overdose perspective. You can take about a 20,000 times higher dose than required to get the effects of LSD and not have any sort of overdose effects of that, right? So that's you know, pretty safe, right? He's like, well, how much of this am I going to take? I would not recommend doing that. I would also not recommend even you know, taking 20,000 times the amount of cocaine you need to have a cocaine high, right? Because that's definitely going to be fatal, right? So we're talking about, again, may not use the word therapeutic index if we're talking about drugs that may or may not have a therapeutic effect, right? You kind of have some strange words you might apply there, but you get the point. A lot of times they'll use this, what they call ED50 and LD50, that's effective dose, in 50% of the animals that are tested, and LD, the percentage that's 50% of the animals that die from that dose. Now that seems like a little bit of a gamble, right? Your doctor says, hey, 50% of the people who've taken this dose actually felt better and 50% didn't. You're like, well, that's not helpful. But then he or she may also say, like, hey, here's a higher dose. You know, 50% of the people that take this are fine. The other 50% died. And unless you're dealing with a pretty severe issue, you're not going to be signing up for that, right? So for most purposes, we're more interested in like a 99-1, right? Like in 99% of the population that took this dose, they felt better. Okay, you're like, okay, I'll take those chances. And then 1% of the population that took this died. That's much better than a 50-50 shot, right? Hey, who loves affinity? That's actually a really good joke, if you knew what affinity meant. What is affinity? It's the likelihood that two things will bind together and not let go, right? So we're thinking about here two molecules that would join together. For our purposes, we're thinking about a drug or a neurotransmitter. binding with a receptor, right? One of the big problems with side effects and medications and things today are the synthetic drugs, right? So the naturally occurring drugs have a certain kind of affinity for your receptors, right? They've sort of developed at the same evolutionary pace that we have. Awesome. We can take that natural drug and I don't mean natural like, you know, go down and like, I don't know, trying to think of something that's a natural remedy that's not effective at all. This doesn't mean like, you know, go rub your face with herbs and it'll cure cancer. That's not what I'm saying. Right? I'm talking about there are drugs, morphine, for example. Morphine may not be the best example. A great example is natural marijuana and synthetic marijuana, which unfortunately is a misnomer like you wouldn't believe, because they left out so much when they created synthetic marijuana. They only give you like one of the like 600 compounds. And they don't give you the ones that keep you from having a psychotic episode. That's why it's really synthetic THC, has so many, such a higher rate of psychotic episodes than naturally grown marijuana, because it doesn't have the same compounds, right? So there was a chemist who was sitting around like, hey, here's the stuff that works, you know, let's tweak that and let's give that to you, not necessarily knowing the rest of what you should be doing in those cases so that you don't like run down the street ripping your clothes off yelling at the police, which happens. Affinity, right? So there's that natural affinity that you might have with that natural substance. If I'm a biochemist or a molecular biologist and I'm sitting around and I'm like, huh, you know what, I bet if I bend to this molecule here and put an extra little thing over here, I can increase the affinity of this drug for the receptor, which is cool, right? Because then maybe I have better pain relief. But maybe I've also just increased the likelihood that that drug is going to be abused, right? Because it's that much more powerful, because it has a higher affinity. It's going to bind more readily, and it's going to bind for a longer period of time, okay? Sometimes that's okay, but you got to watch where that line is, right? All right, there's your dose response curve. Not a big deal. You can imagine this is any drug. How many of you have ever used caffeine? I feel like that's a drug most people are familiar with, right? What happens when you ingest caffeine? I mean, what's one of the things you feel, right? You feel a little energy, your heart rate goes up, right? But there's a cap on that, right? Like you're only going to get so much of a benefit, no matter how much caffeine you ingest. There's a certain point where it's going to plateau, right? Taking more caffeine is not going to give you more effect, right? You're not going to get more energy. You're not going to get a higher heart rate from that. You're going to plateau at some point, okay? So ingesting more beyond that's not helpful. Some drugs have, so caffeine's a good example. Caffeine sort of has a dose response curve that looks like that, relatively flat, right? What's another drug that increases your heart rate, gives you some energy? Methamphetamine, right? Methamphetamine's got a much steeper curve, right? You don't have to take a whole lot of methamphetamine to start getting up there with a higher response, right? A higher effect from that drug, okay? Now, I guess it sort of depends. In this example, which one's the better drug to take? The answer is always caffeine in this case, right? But if this was two other drugs, the answer might depend on what result you need, right? If you need that higher result faster, you might need to take the stronger, more powerful drug, and then that might be something you're willing to take the, take the chance on the risks there. But if it's something safer and slower, you can take your time, then you might be willing to not have as high of a peak response, but you can titrate that response better, right? Does that make sense? It all depends on what you're going for, right? What you're trying to do, what the situation is, and varies from drug to drug.
So this, in a real-world application, would be you going to a doctor and having a recovery problem, and two drugs that can do the same thing, but it's not a big deal, so they give you the steeper one, but then you're an older person that has the same problem, and they give you the stronger one. Does that make sense?
No. I mean, I'm just going to be honest. A recovery problem, you mean like rehabilitation?
Yes.
Like, so you've had knee
They
surgery.
can't give you the stronger one because you'll go back to being addicted easier. Does that make sense? So they give you the smaller curve drug that does the same thing, it just takes longer.
Possibly.
Because I think they do that here when we have such a big drug problem.
Yeah. So if you go in, like let's say you have your wisdom teeth cut out, or I don't know, you have knee surgery. They're not going to go like, whoa, man, let's just unload the biggest opioid we've got on you, right? They're probably going to start a little slower, right? And in particular, if you can do pain relief with non-opioid drugs, that's going to be better because the abuse potential is lower for those drugs. Does that make sense? So yeah, sort of. We'll go with that. Does that help? Okay. You sure? You don't seem terribly confident about that. Okay. Try a confident face. Nobody will know the difference, what's going on inside, but they'll think otherwise. We'll talk about facial expressions someday. We'll practice. Here's a dose response curve. There's your margin of safety, therapeutic index. That's the difference between what works and what kills you. Okay, this is for morphine, right? At a certain point, morphine will actually shut down your breathing. Seems like a bad idea, right? So there you go. Again, you could draw this dose response curve for like Tylenol, right? And you can see how much wider that is. Right. We want to talk about tolerance. We do. What's the concept of tolerance? I think most people understand this, right? As you take a drug over time, you have to take more of that drug to get the same effect, right? The question is, why does that happen? I think that's what's really important for this class. Why does this happen? You're like, oh, well, you just get used to it. Well, that in no way gives you any mechanistic information about that process, right? Like, oh, well, just something happens in your body. Great. I'm going to tell you exactly what happens. There are sort of a couple things that can go on at any given time to develop tolerance. One of those is going to be what we call enzymatic induction. So Wesley, you remember those enzymes in your liver that are breaking down? Guess what happens if you have more of those enzymes? Absolutely. And guess what that does to the length of the effect of that drug and the power of the effect? Right. It reduces that considerably, right? This happens, great example. How many of you have ever ingested alcohol? Don't have to answer that, right? You've got a nice liver enzyme called alcohol dehydrogenase, right? What's that do? It takes alcohol and turns it into something that's not alcohol. Right, so you can recover that Olympic level gymnastic skill that you have. So it's going to break that alcohol down so that you can excrete that, right? As you ingest more alcohol over some period of time, your liver will start to make more alcohol dehydrogenase, right? So that it can continue to break down the alcohol you're ingesting at some rate that prevents you from having negative effects of that drug, right? Because there's this concept we want to think about, homeostasis. I don't know why that keeps disappearing. Okay, homeostasis. You've got kind of a set operating point for all systems in your body, right? Anytime you ingest something, you do something that alters that set point, your body's going to try to return to that, right? Because that's where it operates the best, right? At that homeostatic level, when you're not screwing around with it. Okay? But sometimes you decide, well, I'm going to screw around with this and see what happens, right? And so you decide to ingest some alcohol. You're going to, though, create more enzymes. You're going to try to break that down. Okay? The other thing that you can do is actually at the receptor level. And we'll talk about receptors later. Well, we talked about them a little bit. You can actually, like let's say you've got a bunch of dopamine that's being dumped onto your cells because you're using cocaine, right? That's a good example. What's going to happen over time is you're going to stop making as many dopamine receptors. You're still dumping a bunch of dopamine, but you don't have as many receptors for them. So what do you have to do? You have to increase that dose of cocaine so that you release more dopamine, right, to activate fewer and fewer and fewer receptors to get that same response. Okay? Huh? That's why tolerance goes up, yeah. Absolutely, less receptors. So you're still dumping a neurotransmitter in this case, but there's nothing there for it to act on. So you have to dump more of it to get the same activity level out of fewer and fewer receptors, right? Okay. The problem with this is what happens once you stop using that drug. So in this example of cocaine, I mean, first of all, we should realize dopamine is an is an essential neurotransmitter. It's an essential neurotransmitter to keep you doing things that you should do, right? Every time you take a shower, every time you study, every time you see somebody nice and wave at them, you get a little dopamine boost, right? And it makes you repeat those things. It's important. Sometimes you have landed upon a substance that really powerfully releases that drug or that neurotransmitter, right? And you want to repeat the application of that drug, right? And that's exactly how addiction happens. You just sort of randomly luck upon a substance or a behavior, and you got such a massive release of dopamine out of that, you're going to go back and do it again, right? That's it. It's same brain mechanism that has caused you to repeat other activities that are beneficial, right? Because you get that dopamine release. It causes you to repeat an activity that has some high-level side effects, right? Other problems. So now you've decided, hey, I've realized I've got a problem. I'm going to stop using this substance. Okay? Your body has, for however long you've been using that substance, been working to negate the effects of that substance, right? So you've been pulling back as many neurotransmitters as you can. Maybe you've been creating more enzymes to break down things, right? Whatever it is you're doing, you've got these tolerance mechanisms going on. So now you stop. And now all of a sudden, your dopamine production doesn't go back to baseline. It's below baseline, right? You're not making as much dopamine anymore. You don't have as many dopamine receptors anymore. Guess how you feel right now? You feel horrible, right? Okay, because you're still not at homeostasis. And you have to take time to reverse those processes, right? So if we removed receptors during tolerance, we have to recreate and put more receptors out there during that withdrawal period, right? This is one of the #1 reasons that people relapse. Why did you start using the drug in the first place? To feel better. What happens when you stop using the drug? You feel horrible. So what are you going to do? Well, I'm going to use the drug again because it makes me feel better, right? It's a perfectly normal process, right? And it makes a lot of sense when you think about it that way, right? And you can see how quite easy it is to get into this loop, right, of using or doing things that have some seriously negative side effects because you're getting that primary effect of increasing dopamine levels. All right. There's also the concept of sensitization. This is a little different. This is as you take a drug over time, you become more sensitive to some of the side effects, right? So this is why sometimes maybe you've taken a drug and you've had an allergic reaction to it, and then you take it a second time and you have an even bigger allergic reaction to it, right? That happens sometimes. I don't know if anybody's taken like antibiotics, for example. Sometimes they cause rashes, right? And then the second time around you use that same antibiotic, you'll have an even worse reaction to that. Hey, what about the placebo? Right? Placebo effects, very real, very interesting, very awesome. Doesn't mean that it's necessarily doing anything where you think it is. It's just making you feel better. And I guess as long as you feel better, you're getting your money's worth, right? You can decide what that's worth to you. So often placebos are used as control groups in research. That's a real problem, though. This is why, do you know the last time that we had an antidepressant make it to market? It takes a while, right? And the reason for that is when you compare a drug group to a placebo group and they both see some sort of improvement, then you think, well, what's the point of taking the drug, right? If me just telling you you'll feel better makes you feel as much better as me giving you this drug that should make you actually feel better, why would we run the risk of the side effects, right? We'll just start telling people they should feel better. There are a couple problems with this. One, placebos are not actually treating the mechanistic issue behind the problem, right? Whatever that is. So let's say you have, say you're having some back pain, for example, right? And we give you a placebo or there's some placebo treatment for that. You go and roll around in some salt crystals or whatever it is. Somebody's done that, I can tell by the look, right? Yeah, waste of time. Oh, well, let me rephrase that. Doesn't change your physiology in any way, right? It's not actually going to alleviate the problem. So you might walk away from that and go like, oh, my back feels better. Well, that's not because we've actually treated the problem. It's because we've made you think you're going to feel better, which is perfectly fine, right? If it's not something too serious. Now, if you're dealing with a serious issue, like let's say you've got a tumor, or let's say you've got MS or diabetes or something, you're not going to be able to just like, light up your Himalayan salt lamp and all of a sudden you're going to go like, my diabetes is gone. It's not the way it works, right? You might go like, hey, I actually, maybe you're not experiencing as much, of the diabetic neuropathy. Maybe some of that pain is alleviated, right? But that's a placebo effect. Again, perfectly fine. Even if you know what it is, placebo effects they still work. One of the coolest things with placebo effects, this is a good story, Kyle, so take notes on it on your phone. Actually, Kyle, you've probably heard this story in the psychopharm class, but there was a group who did a study a few years ago, and they gave two groups placebos, right? One group, they said, hey, here's this really expensive drug, and it costs a lot of money. Here's how much it costs. They were obviously getting it for free in the, in the study. But it's a really expensive drug, and you take it, and they rated how much better they felt. And then they had another group, and they said, hey, here's this drug. It's really cheap, but it's really effective. It works really well. They gave that drug to the other group. The group that thought they were taking the more expensive drug actually felt better after the fact, even though neither of them were effective drugs that should have alleviated any issues. The folks who thought they were getting the more expensive drug actually reported feeling better afterward. So there you go. You're just constantly getting ripped off. That is really cool, isn't it? So what you should do is just buy, this way they always tell you, buy expensive bottles and put cheap things in it, and just tell people it was something expensive, and they'll think the same about it. Save you some money that way. Right, Sydney? All right, so there are a lot of things that affect placebos, placebo effects. Again, I think the point is don't abandon things that actually will solve a problem. But if there are other things you're doing that seem to work, well, yes, you can keep doing it. It's not going to bother me. All right. Now we want to talk about things called agonists and antagonists. I'm going to slow down here because for some reason this really confuses people. And you're thinking, I know you're sitting there and you're going like, well, this is so easy. They're two completely different things. And how many weeks is it until the exam, Kyle? I don't know. However many weeks it is, you're 5. That's not necessarily 100% true, but let's say it's 5 weeks. I don't know how many weeks it is. You're going to forget, and you're going to get confused, and you're going to tell me the wrong thing. Okay, and I want to make sure you tell me the right thing. It's so much easier to grade exams that are right. It is. It makes my life easier because I don't have to yell at Kyle as much. What is an agonist? Very simply, an agonist increases the effect of a neurotransmitter. That's it. Okay. There are a million ways, not really, but there are a handful of ways that this can happen, right? Anybody football fans? Who's a football fan out there, right? How can you make your team better? Well, there are a lot of ways, right? What if you cut a guy who's not any good? What if you trade for a better player? What if you have a good player on your bench, but you finally start paying him what he's worth so he plays better, right? What if you move to a new city where you've got a better fan base that's going to support ticket sales and can support you to purchase contracts of players who are out there who are better, right? These are all things you can do to improve your team. These are all agonists, right? They're different. They work in different ways. Sometimes you're adding a positive thing. Sometimes you're getting rid of a negative thing. Maybe you've got a guy on your team who's really toxic, right? He's got a bad attitude, and he's making the rest of your team worse. If you get rid of him, your team gets better all of a sudden, right? No, you got rid of a really talented player. That's an agonist. That's an agonist action because we're making things, we're increasing, right? The opposite of that is an antagonist. And this is just going to reduce the effect of a neurotransmitter. This is a way to make your team worse. Okay? You could move it to Cincinnati.
to make it any worse than it is.
I guess it's not. But there are things you can do to decrease the effectiveness of a neurotransmitter. That's going to be an antagonist. Even if we think we're increasing something, if the end result is a decrease, that's an antagonist. Okay? I don't care what the immediate action is, it's that end result on that neurotransmitter. Okay? Here's a great example. There are precursors to dopamine, L-DOPA. That's going to be an agonist because we're going to increase the amount of dopamine that's available because we're giving you more pieces to make that. There are enzymes that break down dopamine, and if we can deactivate that enzyme, right? If we can prevent the breakdown of dopamine, even though that seems like we're inhibiting something, right? We're inhibiting an enzyme, but the end result is we have more dopamine because we're not breaking down dopamine as much, right? Both of those are going to be kind of like agonist actions. All right, so we can do stuff there in the construction of a neurotransmitter. We can also affect the way that we store neurotransmitters, right? So if we start affecting vesicles, right? Are we moving vesicles faster? Are we blocking vesicles, right? That can be an agonist or an antagonist. If we can move those vesicles faster and release them, it's going to be an agonist. We're going to release more neurotransmitter, right? If we block the release of the vesicles, that's going to be an antagonist because we're blocking that effect, right? That action of that neurotransmitter. What about things at the terminal button, right? All right. How many of you have heard of botulism toxin? Right? Yeah. Botox injections, right? You get these for a lot of things. I'm worried I'm going to have to get them someday from dealing with students and making this face, right? It's going to give me a bunch of wrinkles, right? Yeah. You know about this, right? I mean, it happens. So I'm going to have to get that taken care of at some point, Kyle. You can get Botox injections for other things. They do it for migraines now, right? So that works. Other sort of muscular issues. It actually prevents the release of a drug so you're not contracting your muscles anymore, right? So it's going to prevent the release of acetylcholine in that case. You can also trigger the release of a neurotransmitter, right? Alcohol does that. Cocaine, your amphetamines do that. This is actually a pretty important diagram. It's a little fuzzy, okay? But in your book, it's hopefully clear. What I want you to take away from this, again, is not like each specific case of what's an agonist or antagonist. I'm going to ask you to memorize specific examples. I don't want you to go, oh, well, this is an agonist. That's going to be useless to you, right? What's going to be helpful to you is knowing what's the action, right? And based on that action, you can tell me if it's an agonist or an antagonist. That's what I really care about, right? Again, there are going to be agonists and antagonists that are discovered and developed over the course of the next maybe even 6 weeks. Who knows, right? What I want you to know is not the names of all agonists and antagonists, but just what they do. And if somebody says to you, this is a dopamine agonist, first thing you're going to know is that's going to increase the action of dopamine, right? And then if they say it's a dopamine agonist because it interferes with the breakdown of dopamine, then you know something about that, right? That concept is important. The name of that particular substance, well, they'll tell it to you. You can look that up, right? It doesn't matter. I want you to understand the concept of what's going on. Does that make sense? Okay. Only 75 slides to go. There are more than 75 slides in the rest of this class. Not today, but just over the course of the semester. All right. There are different kinds of binding, right? We'll talk about that. So there are what we call direct agonists or direct antagonists. These are drugs that bind right into that neurotransmitter binding site. So instead of, for example, dopamine binding here, okay, instead of dopamine binding, we're going to have a drug bind there. Does that make sense? It binds directly. There are other drugs that don't bind directly. They're indirect. They bind at a different site. You still have the neurotransmitter binding site. That's still available to you. Okay? Doesn't matter. We have another site where that drug's going to bind. Now, these two types of binding are referred to as competitive binding. Both the drug and the neurotransmitter in this case are competing for the same binding site, right? So it's a fight. Who's going to bind there, the drug or the neurotransmitter? Which one? Okay. What affects this process? Affinity, right? Who has the higher affinity is going to be who's more likely to bind. What's the concentration of the drug versus the neurotransmitter, right? These are all factors that are important. What's more powerful than competitive binding is non-competitive binding, okay? In this case, it does not matter if the neurotransmitter binds or not. Why? Because there's a separate site for the drug to bind. The neurotransmitter can do whatever it wants to do. The drug's going to do what it does because there's a separate site where it binds. Okay? Not competing at all for the same sites. Okay? Non-competitive binding. Does that make sense? Okay. It's kind of like, you guys know about contracts, right? You guys heard of non-competitive contracts. That's when somebody just decides, I'm going to give this contract to my brother-in-law because he's my brother-in-law and I don't really care what anybody else does. And then there's competitive process where people pitch their ideas and their costs, right? Competing for the same thing. All right. There are sort of two ways to end this process. We already talked about these. We talked about reuptake and enzymatic destruction, right? Or enzymatic degradation, whatever you want to call it. Keep these in mind, right? At the end story here, this is another place where we can sort of process or change the effects, right? So if we block reuptake, if we increase degradation, these are all things that can change the effect. All right, let's spend a little bit of time talking about some specific neurotransmitters and neuromodulators. There are probably 50 neurotransmitters out there. You don't need to memorize 50 of them. 48 of them are important. The other two you can forget, right? Now, there are 4 or 5 sort of heavy lifters we want to think about, right? The others, sometimes they're neurotransmitters, sometimes they're not. Next week, there might be 52, right? They're constantly finding new things that have action in your brain, which is really awesome because that means there's like new stuff to know about how your brain works, right? There's not a whole lot of new stuff to know about, like, I don't know, how rocks work. Is that a thing? I think we kind of figured that process out, right? But your brain, we're still working on it, so hang in there. Hey, what about glutamate? This is the main excitatory neurotransmitter in the brain. There are a couple different kinds of glutamate receptors, NMDA and AMPA, right? Some of those are inotropic and some are metabotropic, which is kind of cool. How many of you have ever ingested glutamate before? Everybody has. It's in stuff. You need it, right? It's a pretty important amino acid. How many of you have heard of this guy? Yeah, monosodium glutamate, right? We'll talk more about that later when we talk about taste. You should eat as much of that as you can. It doesn't really matter. I mean, too much sodium is bad for you, but otherwise you're fine. Hey, what about GABA? This is gamma aminobutyric acid. This is actually made through the same process as glutamate. There's like a little side trip it takes. I should tell you this. Glutamate is excitatory. What does it mean if it's excitatory? It opens ion channels for positively charged ions, sodium and calcium. GABA is inhibitory, so it's going to open chloride channels. Anybody familiar with the action of benzodiazepines? Okay. One of the main effects of a benzodiazepine is sedation, right? Why would you give someone a benzodiazepine? They're sort of in the middle of a crisis, right? And you need to get them like from this to this, right? Shouldn't take benzodiazepines. I always throw this out there, Kyle, because you probably see people, right? You see they've been on a benzodiazepine for 2 years. Yeah, you shouldn't be on a benzo for more than 19 minutes. Right, that's about the time course of how long you should take a benzodiazepine. If you're still on a benzodiazepine, get a different doctor. I'm just going to say it, right? Because you shouldn't be on one. You should find other things. Benzodiazepines are heavy lifters. They're tough. They open chloride channels, basically shut you down pretty quickly, right? Which is, sometimes you need those, right? Sometimes you need that quick action, get somebody down. You don't want to stay on those things. So that's GABA. Here's glutamate and GABA. We should talk a little bit about some other neurotransmitters. Acetylcholine is important. We'll talk about it for muscle contraction. Also when we talk about learning and memory and sleep. Dopamine, movement, attention, learning, planning, problem solving, does a lot of stuff. Epinephrine, norepinephrine, keeps you pumped up. Serotonin, who loves serotonin? Great for mood regulation, yeah. Also important for sleep and impulse control. Histamine. We talked about antihistamines last time, right? Somebody asked about histamine. Is that true? Benadryl? Who asked about Benadryl? Oh. Huh? Okay. I thought you thought it was somebody else. I thought that was going to be weird if you remembered what somebody else asked, but I think it might have been you as well. Again, antihistamines sort of block that. Opioids. Hey, you do have opioid receptors, and you create endogenous opioids, right? You create opioids in your body. If you want to create some, great way to do it, stub your toe. Fastest way to make opioids ever, right? You're going to make a lot of them. You're not going to make really powerful ones. It's not like you're going to stub your toe and get heroin. You're going to stub your toe and you're going to get an endogenous opioid out of that, right? What about endocannabinoids? Yeah, you make those as well, right? That's why cannabinoids work, because you make something similar in your own body, right? And because you make something similar in your own body, the exogenous chemical that you take can have some similar effect, right? Endocannabinoids, mostly right now we think about them with appetite regulation, right? Okay. This is one of the uses for medical marijuana, or folks with like wasting diseases, right? Where you're losing a lot of weight, you're not hungry, you don't feel like eating, right? If you ingest a cannabinoid, right, it's going to stimulate your appetite, and you'll eat more and potentially gain weight. There you go. Interesting story, right? Here's an NMDA receptor. This is just showing you up close what a receptor kind of things that we have. Got your spot for your glutamate. You got your calcium, goes through it. Interestingly, with NMDA, you do have magnesium there. We're going to talk a lot about NMDA receptors when we talk about learning and memory, so don't think too much about them right now. We want to spend a small bit of time thinking about GABA receptors. What's interesting here is you have sites for benzodiazepines. Whoa, what's this mean? You've got a GABA site and a site for a drug. What kind of binding is that? Non-competitive, right? Yeah, it's non-competitive because it doesn't matter if you have GABA or not, that benzodiazepine will jump on and do its business. Okay? Also, barbiturates will grab on there. Don't worry too much about acetylcholine. Here's a bunch of drugs that affect glutamate and GABA. You can read those whenever you would like. What about acetylcholine? You've got acetylcholine going a lot of places, right? Most of it kind of starts back here in the blue place. Locus ceruleus, right? Means the blue place. Since acetylcholine a lot of places in your brain, a lot of that's going to happen up in the cortex. That's why we're going to think about that with sleep and learning and memory, right? A lot of cortical activation. Here is the production of acetylcholine. You take your choline, you take your acetyl coenzyme A, stick it into some chat, and the next thing you know, you get acetylcholine and coenzyme A. Then you got to break it down, so you have to have acetylcholine esterase. This is the guy that takes acetylcholine and breaks it down into acetate and choline, right, which is really an important process. Here's some drugs that act on the acetylcholine system. There is your Botox, right, which prevents the release of acetylcholine out in that peripheral nervous system, so you're not releasing acetylcholine onto the muscles, so the muscles aren't contracting, right? So you're not furrowing your brow, you're not clamping up your skull muscles, giving yourself a headache, right? Not clenching your jaw, working up a TMJ issue. Okay. How many of you love black widow spiders? Those are pretty cool, right? Yeah. How many of you have one at home? You just keep a pet, right? Annoying neighborhood kids come by, you throw it at them. But he does that. You should. It's a fast way to get rid of annoying neighbors. Well, briefly. So you get rid of them, and then their parents show up, and then you throw spiders at them too. And then nobody comes back. You only have to throw spiders twice. I tested that. So what happens here? This actually stimulates the release of acetylcholine. So when you got this venom in you, you dump out a bunch of acetylcholine, and so you kind of have a convulsion, and then guess what happens? Well, you can't move anymore. You've depleted your acetylcholine store, right? So that happens. Yeah. That's fun, right? There you go. Hey, who loves monoamines? Mostly we're talking about dopamine here. It's a different neurotransmitter. There's a whole class of drugs called catecholamines. I'm not going to ask you about that. It's related to the shape of the drug, right? The shape of the neurotransmitter. They're called catecholamines. There's this guy called L-DOPA, right? L-DOPA is a precursor for pretty much all of your catecholamines, but particularly dopamine. Individuals with Parkinson's disease, one of the major treatments for that is to give them L-DOPA, right? They're not making as much dopamine because those cells are dying. Let's give them more of the things they need to make dopamine so they can make a little more dopamine for a while. Now that's got some limited action, right? The reason that has limited action is because if you're still losing cells that are making dopamine, I mean, at some point, that's not going to work for you, right? Also, there's a problem with sort of giving someone a neurotransmitter systemically, right? One of the cool things about neurotransmitters is even though we only have a handful of these, we can release them in little places, different places all over, right? And so when you just flood someone with dopamine, they get dopamine everywhere. We're not just giving them dopamine in that nigrostriatal pathway, we're giving them dopamine elsewhere. And one of the problems with getting dopamine elsewhere is you start to develop schizophrenic symptoms. As you increase dopamine levels too high, you start to have hallucinations, you start to have delusions, so you develop some of those, what we call the positive symptoms of schizophrenia. We'll talk about that some as we get through this semester. Again, norepinephrine and epinephrine, not a big deal. Here's some other monoamines for you there, not a big deal. Don't worry about that. Here is the dopaminergic pathways. There are 2 or 3 of these. Here's that nigrostriatal pathway, right, going from the substantia nigra to the striatum. You also have something going from the ventral tegmental area. In particular, one location for that drop-off is the nucleus accumbens. This is the brain circuit that is involved in addictive behaviors or in learning to repeat a behavior, right? However you want to think about this. Anything that you do that makes you feel good is going to take dopamine and dump it into the nucleus accumbens, whatever that is, right? If what you did that made you feel good was cocaine, that's exactly what happened. If what you did that made you feel good was, I don't know, clean up the trash on your street, there you go, right? One of those will give you more dopamine than the other. But you guess which one it is. This is why you don't see a lot of people addicted to picking up trash. You don't get as much dopamine out of it, right? So you have to be careful. Don't worry about this. Monoamine oxidase, I mean, that just breaks down monoamines. It's not a big deal. You already know the story, right? If it's enzymatic deactivation, it's enzymatic deactivation. Monoamine oxidase takes a monoamine, chops off some stuff because it's got that ACE. It's no longer that monoamine. Guess what it does? Not monoamine stuff, right? So it doesn't have that effect anymore. Here's norepinephrine. Here's your norepinephrine system. Again, we're going to think about cortical arousal, so we're going to have, again, coming from the blue place up there. Serotonin, we should talk about this briefly. We'll talk about serotonin quite a bit through the semester. Abbreviated 5-HT because it's got this fun long name right there. So you can write 5-HT if you'd like for serotonin, save you a little bit of time. I know, ink is a high commodity, so you want to save as much ink as you can, so you use abbreviations. What do we know about serotonin? Well, plays a role in about everything, right? So you think about drugs like Prozac, right? That's a drug that's going to block the reuptake of serotonin, so it makes more serotonin available for you. Here are your serotonin releasing nuclei. You can kind of see all the fun places that serotonin goes. Histamine, don't worry too much about that. Histamine's largely involved in keeping you awake. There's like a whole breakdown of monoamines and different drugs you can take to affect your monoamine system. All right, let's talk about neuromodulators briefly, right? So you get the idea of a neurotransmitter, binds to a receptor, makes that receptor do something, right? A neuromodulator is something that's similar. It'll bind to a receptor. It in and of itself will not drive an action for that receptor. What it will do is it will make the action of that receptor occur more easily, or make it less likely to occur. So that neuromodulator can just modulate activity that's already occurring. It can't drive activity itself. It can only modulate the activity that's going to happen, right? Does that make sense? Okay. So there you go. Not a big deal. And there's some different kinds of neuromodulators and whatnot. Questions about that? Anybody doing the quizzes? How many of you have done the quizzes? Oh, great. That working okay for you? Okay. It's a fair answer.